Kahler and Hyperkahler.
Great, thank you. Well, it's very grateful to the organisers for the opportunity to speak. This is obviously a great honour, and it's particularly nice to speak in a conference in memory of Professor Chern, who of course was one of the creators of modern differential geometry, especially complex differential geometry. So it's great to be able to speak here. So there's certainly a relationship between what I'm going to talk about and what Amichai talked about in the preceding talk. In deference to the general audience, I'm actually going to start off in a very, very elementary way, just to give a general idea of some of the concepts. And then later in the talk, I'll get on to some of our current work. But the first few slides are going to be extremely general. So the projects we're working on are summarized in these two archive preprints. And there are my collaborators, Amichai, Francis, Antoine, Julius, and Zhenghao. Great. Okay, so what are we doing? We're doing differential geometry, which we could very informally describe as the study of geometric objects, of shapes, of spaces, but of course of arbitrary dimension. We're usually looking at objects called manifolds, which we could intuitively think of as smooth shapes. So in dimension 1, things like the circle or the line, the real line. In dimension 2, the sphere, the torus, more informally the donut, and then of course versions of the donut with more than one hole. So the geometric classification is finer than the topological classification. So just an example of this, the sphere, we could obviously squash to form an ellipsoid, but because that's kind of a continuous deformation, there's no tearing or creating holes or whatever. Those are the same topologically, but they're not the same geometrically. So the study of differential geometry really goes beyond topology. We're looking at some extra data, more refined concepts that distinguish between shapes that may be topologically the same. So we need a gadget to express geometric data, things like lengths, angles, volumes, curvature, and so on. So this is what differential geometry is really about. And in fact, we can actually get a sense of what's going on just by going back to high school and looking at some elementary concepts from Euclidean geometry. Because what do we have in high school geometry? It could be dimension 3, but this also makes sense in higher dimensions, of course. Well, we have this thing called an inner product, or a dot product, or a scalar product. In my school, we called it a scalar product. So written as x dot y, where x and y are two vectors, or maybe using the left and right pointy bracket notation. And that actually is the object that tells us about lengths and angles and so on. Because the length, of course, the vector, that's just given by the positive square root of the inner product of x with itself. And of course, that means we can talk about the angles, because of course, thinking back to high school, we have this elementary formula relating the angle, the cosine of the angle, to the inner products. If we know the inner product of the vectors x and y, and we know the lengths of x and y, the inner products just themselves, or the root of that, then that determines the angle. So in a sense, differential geometry is about taking this elementary data from high school geometry and generalizing it to the general curved higher dimensional situation, if you like. So what can we do to generalize that discussion? Well, first of all, the classical Euclidean inner product would be given by that formula. In matrix language, we could think of the inner product of x and y as x transpose y. That would generalize, we could replace that by x transpose ay, so written in index notation like that, where A is a general symmetric matrix, but also, of course, required to be positive definite, so that x inner product x is always bigger than or equal to 0 and equals 0 only if x is 0. But now the key insight is the coefficients, if you like, the a's and Euclidean space would be constant. But now, working on a general space, on a general manifold M, we allow the coefficients of the inner product to vary to, if you like, be functions on the space M. And this is the key concept. This gives us the concept of a metric, or precisely a Riemannian metric, because it's positive definite, which we could write as an expression like that. Sometimes people would put a tensor sign in between the dx I and the dxj. And the point is, this is just a sort of global version of the inner product, what I wrote up at the top of the page. But now the inner product is varying from point to point on our manifold, because the gij are no longer constants. These are actually functions of our local coordinate system x1 through xn on manifold. So now the primitive concept of the inner product of two vectors on Euclidean space would be replaced by gxy. That is what we get by applying the metric. So the metric is the correct generalization to a general manifold of dimension n of the Euclidean product, inner product of high school geometry. And this now enables us to talk about lengths, angles, volumes, etc. on the manifold. Well, I said curvature, ultimately we want curvature. And in fact, with a bit more work, you can show that the curvature information on the manifold is expressible in terms of this gadget, the metric. So just for fun, and to give a bit of a sense of the complexity of the subject, I actually wrote down the formulae here. The curvature information on the manifold is expressed by the Riemann curvature tensor. And this, the key thing to take away from this, of course, is this depends in a very non-linear fashion on the metric and also on its first and second derivatives. So the first step is to define the Christoffel symbols, the gamma kij, which you see, again, that's a nonlinear expression involving first derivatives of the metric. But then we now have the full the curvature tensor, which involves derivatives and quadratic expressions in the Christoffel symbols. So overall, this depends on the metric and its derivatives up to order 2. So the precise formulae aren't so important. This is sort of a thing that most people will be familiar with as a kind of curvature object, a derivative bit plus a quadratic bit. But the key point is that any kind of curvature conditions on a manifold, on a Riemannian manifold, will become nonlinear systems of partial differential equations and the metric coefficients. And this, in a sense, is why differential geometry is so complicated, because we're getting these complicated nonlinear PDE systems out. So things like the Einstein equations, for example, this is in general a nonlinear PDE system and hence difficult to analyze. So this sort of gives a sense about where the complexity of the subject comes. Well, that's one bit of data. That's the metric. This sort of tells us tells us about lengths, angles, curvature, etc. If we're getting into Kahler geometry, then there's another bit of data we need, complementary to that, which is the idea of a complex structure. Now, again, it's profitable just to go back to very elementary Euclidean geometry here. Suppose we're working in the complex plane, so R2, the plane, but now viewed where the points are viewed as complex numbers, a plus ib. Well, if we have a vector, then of course I can multiply that by I, and that just rotates it through 90 degrees. So the key point for our purpose is that x is orthogonal to ix, and x and ix have equal length. So again, we can just take that elementary concept and now globalize it to the concept of a manifold. So a complex structure on a manifold, roughly speaking, is something that generalizes the idea of multiplying by I. So what should that be? So that should be a map of tangent vectors on the manifold. So don't worry about the notation. Tm basically just denotes the manifold and the various tangent vectors to the various points of that, the tangent bundle of the manifold. So the complex structure should be a map, linear map I, that has a couple of properties. For a start, it should square to minus the identity. That makes sense, because if we multiply by I and multiply by I again, then we're just multiplying by -1. So it's a linear map that squares to minus the identity. How does it tie in with the metric? Well, as we said, multiplying by I should preserve lengths in the metric. So we would hope that it would be good to consider metrics that are compatible with the complex structure, in the sense that G of Ixy, the inner product of Ixy, is the same as Gxy. Now, there's also a slightly more technical condition, the integrability condition, which basically says that we have local holomorphic coordinates coming from this complex structure. So it's a short talk, I won't get into that. But if we have all these things together, then we have a complex structure and an associated metric that is what is called Hermitian. So that's just saying basically that applying I does not alter the inner product. Now that has a couple of elementary consequences, of course. Let's look at Gix, x. Well, by the Hermitian property, that's the same as Gix, ix. You can just hit both of those with I. But then I squared is -1, so that's minus Gxix. And by symmetry, everything is symmetric, of course, by the inner product property. That's the same as minus Gixx. So G of Ix, x is equal to its negative, so is 0. So that recovers, if you like, the condition we had before, that x is orthogonal to Ix. We could push that argument a little bit, further, applying essentially the same argument to Gix, y, the inner product of Ix and y in the metric. That tells us that this is equal to minus Gx, iy, which by symmetry is minus Giy, x. So that means that the object, the tensor we form, omega, defined by saying omega x, y, is the metric applied to Ixy, that is actually alternating. Omega of xy is minus omega of yx. So of course that kind of tensor has a special significance, an alternating or skew-symmetric tensor, that is a differential form. So we have a differential two-form omega, written in local coordinates like that, associated to the metric and the complex structure, provided they're compatible in the sense on this slide, provided they form a Hermitian structure. So that's Hermitian geometry. In practice, it's nice to consider a slightly more restricted, particularly well-behaved class of Hermitian manifolds, the so-called Kahler ones, where the form omega is closed. So that makes the G and the I, the metric and the complex structure, tie together in a particularly nice way. And some of the most basic examples, like Cn, just flat complex space, or in some ways more interestingly, Cpn, the complex projective space, have Kahler metrics, and therefore any complex submanifold of them also has a Kahler metric. So any nice submanifold defined by holomorphic equations. So in particular, some familiar geometric objects, Riemann surfaces, elliptic curves, their higher genus variants, higher dimensional things, nice things like complex surfaces, K3 or Enriquez surfaces, rational and rational surfaces, and so on. These will have Kahler structures, or K3 surfaces will have Kahler structures, and the Okay, so those are the sort of the class of complex geometric objects we consider the Kahler manifolds, and these have a have a physical significance as well. Can we go beyond the complex numbers? Well, yes, we can, because there is an interesting number system, of course, that extends to complex numbers. That's Hamilton's quaternions, named H in his honor. So this is four-dimensional over R in the same way that complex numbers are two-dimensional. We now have not only sort of A plus IB, but we have A plus IB plus JC plus KD, where C and D are real numbers. What's the algebra of the IJK? Well, these, in some ways, these behave a bit like the ordinary I. They square to -1. But now they don't commute, they anti-commute. Ij equals k, but ji equals -k, and we have the analogous relations under cyclic permutation. So this was Hamilton's insight eventually, that the correct number system, enlarging complex numbers, you have to sacrifice commutativity to get something interesting. This was the roadblock that held him up for a long time, but eventually he realized you have to sacrifice the commutative property. So this, it's not at all sort of obvious, but actually it's true that this number system actually has its own geometric analog. And these are the so-called Hyperkahler manifolds. So we now have a triple of complex structures, IJK, that satisfy the quaternionic relations that we have there. Ij equals k equals -ji. And of course, because these are supposed to be compatible with metric, we now have a triple of forms all required to satisfy the Kahler condition, omega sub I, omega sub j, omega sub k. Examples. Well, this actually took quite a while to discover, essentially because unlike the Kahler property, the Hyperkahler property is not really hereditary in a nice way, that you tend not to get such interesting Hyperkahler submanifolds of a Hyperkahler ambient space. In particular, just looking for quaternionic submanifolds of Hn doesn't give you very much that's interesting. Moreover, the associated projective space, HPN, the compact version, if you like, is not actually Hyperkahler. It satisfies another interesting geometry that has some relations to it, quaternion Kahler, but it is not Hyperkahler. In fact, Hyperkahler manifolds are examples of Einstein manifolds. They're always Ricci flat, in fact, and HPN, although it's Einstein, is not Ricci flat. So the correct, well, one of the best ways, not the only one, but one of the best ways to produce Hyperkahler manifolds is by a quotient construction. As it's a short talk, there isn't time to go into detail about this, but the idea is we have a group acting on a Hyperkahler manifold, preserving the Hyperkahler structure, and we can't get a Hyperkahler structure just by naively taking the orbit space, the quotient of that. What we can do, however, in good situations is to form this thing called a moment map or a momentum map, inspired by ideas from Hamiltonian mechanics. That's valued in the dual of Lie algebra, tensor R3. And then we take the zero level set of the moment map, and then we mod out that by the group action, and that turns out to be Hyperkahler. And the power of this method is, the point is, that you can start off now with a very simple space like flat Hn, but then when we take the Hyperkahler quotient, we can get something non-trivial. In particular, a simple example is if we take H2 by circle action, then we get Iguchi-Hansen, the Iguchi-Hansen metric, one of the first non-trivial Hyperkahler metrics to be discovered, living on the cotangent bundle of CP1. So that's the point about the Hyperkahler quotient construction, that you can start off with something very simple, but you get very non-trivial Hyperkahler spaces out of it. Okay, well now I get up to what we're researching, and now I make contact with Amikai's talk. It turns out that for Hyperkahler spaces, there's a very interesting kind of duality. So Ali alluded to this in his talk. It's the duality between Coulomb branches and Higgs branches. And certainly for a large class of Hyperkahler spaces, roughly speaking, these Hyperkahler cones or possibly deformations of them, they come in pairs. We have this duality between them coming from physical considerations. Now, this is actually quite a strange kind of duality. In particular, it can change the dimension. So there, of course, that's different from sort of classical mirror symmetry of Calabi-Yau threefolds. Now the dimension of the Higgs branch and the Coulomb branch can be different. So these spaces are actually living in different dimensions, but they're still linked by this duality. We'll see an example of that in a second. And in particular, one of the ideas is that the deformation parameters on one side should correspond under the duality to the Cartan algebra, the algebra of the maximal torus, if you like, sort of abelian part of the symmetry group on the other side. So in more physical language, the phi at Iliopoulos parameters for the Higgs branch would correspond to the Cartan algebra of the symmetry group of the Coulomb branch. On the other hand, the mass parameters on the Coulomb side would correspond to the Cartan algebra of the symmetry group of the Higgs branch. So one case where we can illustrate this very nicely is the abelian case, so-called hypertoric varieties. So these are sort of the Hyperkahler analog of classical toric varieties. We take flat space HD, d-dimensional quaternionic space, and we Hyperkahler reduce now by an abelian group by a torus n of dimension d minus n. So we have this exact sequence. And then, of course, the residual, we have a residual action of the quotient Tn, which is Td mod n. So what does this give us? This gives us a Hyperkahler manifold of real dimension 4n, quaternionic dimension n is perhaps a nice way of thinking about it, with Tn action, sort of a maximal action of an abelian group. And then we have deformation parameters. There are d minus n of them because the deformation parameters are essentially the parameters on the torus that we mod out by. So this actually, like most things involving toric geometry, actually has a combinatorial interpretation. The n is basically defined by a collection of d vectors in Rn, and then various sort of affine hyperplanes or affine subspaces of Rn tell you where you are on the space of deformation parameters. So basically, we're getting out a fairly simple kind of duality here. The duality between the Higgs and Coulomb branches is, very roughly speaking, you could think of it as swapping the role of the n and the Tn of the subtorus and the quotient. More precisely, we're just dualizing that exact sequence. So what do we have before? With the Higgs branch, we have d minus n deformation parameters and Tn symmetry. When we dualize, as I say, we're swapping the roles of the n and the Tn. So d minus n and n get swapped, and then we're getting n deformation parameters and a d minus n torus. So this is a combinatorial interpretation. It actually turns out that this duality turns out to be something called a Gale duality, which has been around for a few decades in combinatorial convex geometry. But I think actually may even have arisen in the theory of linear programming originally. So there's some very nice classical convex geometry here. Okay, that's the abelian case. In the non-abelian world, things get a lot more complicated. So on one side, we have the Higgs branch, Hyperkahler quotient of the linear space by compact K, quiver variety, if you like. On the other hand, we have the Coulomb branch, which is supposed to be birational to the cotangent bundle of the dual complex torus of K, modulo the var group. So the language here is the classical model for the Coulomb branch would be that singular space exactly, that sort of flat thing modeled out by the var group. The genuine Coulomb branch, there are some quantum corrections which mathematically are represented by the birational transformations. That's sort of the link between the mathematical and physical viewpoints there. So in particular, that gives us a nice check on the dimensions of how the dimensions of the Coulomb branch and the Higgs branch are related. Okay, so we've been looking at a family of examples because there's a nice kind of space called the Hyperkahler implosion associated to a group that fits into this duality framework. So this is a Hyperkahler, or at least holomorphic symplectic space with Kc cross Tc action of the complexification of K and of its maximal torus. The dimension is equal to the dimension of Kc cross Tc, so that's the dimension plus the rank. And this is sort of a master space. If we complex symplectically reduce by the Tc action at the various level sets, we get the so-called constant varieties living in the Lie algebra. And in particular, reducing at 0 gives the nilpotent cone of dimension dim Kc minus rank Kc. So the constant varieties in the SUN case, they're basically just what we get by fixing the eigenvalues of an element of the Lie algebra. In particular, if we fix the eigenvalues all to be 0, then we get the nilpotent cone. So this is sort of a master space with this torus action, such that the reductions by the torus action give you the various constant varieties, in particular the nilpotent cone. It fits into something of great current interest in algebraic geometry. It's an example of a non-reductive quotient. We can think of it as a complex symplectic quotient of the cotangent bundle of the complexification of K, which is a Hyperkahler space with a K cross K action, and then we're complex symplectically reducing by this non-reductive group, the maximal unipotent, or strictly upper triangular matrices, if you like. So this should fit into the duality picture. In particular, in the SUN case, we actually have a quiver variety description of the implosion as a Hyperkahler quotient of a linear space at level 0. So this should give us the Hyperkahler cone. This should fit into the Coulomb branch, Higgs branch picture. So what might the dual look like? Well, we just have to recall a little bit of technology about duals of quiver varieties. If we have a unitary quiver, then to each of the gauge nodes, we can associate the so-called balance. And a node is balanced if the balance is 0. So if the twice the dimension of that gauge node equals the sum of the dimensions of the adjacent gauge nodes. And the idea is, we said before that deformation parameters on one side should correspond to the abelian part, if you like, the Cartan algebra of a symmetry group on the other side. This refines that idea by saying actually that Cartan algebra can now be thickened up to a bigger reductive but not necessarily abelian group. And the yoga about the balanced nodes tells us how to thicken up the Cartan algebra to the appropriate non-abelian reductive group. More precisely, the balanced nodes should give you the Dynkin, that configuration should give you the Dynkin diagram of the semi-simple part of at least a subgroup of the symmetry group of a dual variety. So just to conclude, that gives us a clue about how to figure out the dual of the implosion, first of all in the SUN case. So we need a SUN across Tn-1 symmetry. So the idea is we take the quiver for the nilpotent cone of SUN, we excise the n-dimensional flavor node at one end, and that now unbalances the next node. So to rebalance it, we just put in a bouquet of n one-dimensional nodes attached to it. So now the balanced nodes form an n-1 diagram as before, which by the principle on the previous slide gives you an SUN symmetry. The unbalanced nodes, the nodes of the bouquet, give you the desired abelian symmetry, the Tn-1 symmetry. So there are many computational checks and checks coming from special cases that one can make. In particular, the monopole formula that I talked about in his talk, that enables us to compute things like the Hilbert series, the dimension, the symmetry group of the dual, and everything works out correctly. And there are certain special cases like the n=3 case, which give you nice cross checks as well. So this gives us a good candidate for the dual of the implosion for SUN. And in fact, we now have similar candidates for the Coulomb branch of the implosion for the DN and BN case. Again, the idea is we start with the quiver of a nilpotent cone, then we excise the flavor node, and then we to rebalance the remaining nodes, we then stick in an appropriate bouquet of abelian nodes, and again one can perform the appropriate checks, and everything works out. Great. Okay, so that was a rapid tour from some very elementary things to current research, but I hope that was appropriate for this meeting.
Thank you very much, Anshu. I wish that was a very nice overview of differential geometry, and I wish that my undergraduate differential geometry professor, who was clearly mad, could give such a clear overview of geometry.
Oh, thank you.
I will tell you in private later who he was. He's no longer with us, but he was a completely mad mathematician.
I think this was at Princeton.
Yes. You can probably guess who that might be.
I can guess who that might have been.
Are there any questions from anyone in the audience? So just unmute yourself or okay. So if not, maybe I can ask a quick question. Sure. Is there, and of course, a natural question is that what I know nothing about this. Is an Octonian version of all of this story?
Right. That's a good question, actually. Not really. So of course, what's underlying this is the classification of holonomy groups. So to each Riemannian manifold, by considering essentially the group generated by parallel transporting around various loops, we get a certain group of linear transformations that will be contained, well, in a simply connected case, contained in the special orthogonal group. And for a generic metric is the special orthogonal group. So Kahler, of course, means that we have its complex structure is actually parallel, if you like. The parallel transport commutes with I, it is complex linear. So that means that the holonomy reduces to the unitary group. Similarly, in the Hyperkahler case, the parallel transport is now quaternion linear. It commutes with the three complex structures I, J, K. So that means the holonomy group restricts to the symplectic group SPN. Now we don't, in general, we don't have an octonionic analog of that. So there are a couple of low dimensional spaces which could be viewed as the octonionic projective line and projective plane. So I guess those would be S8 and F4 mod spin 9. But those are actually just symmetric spaces, so they're included in the special part of the holonomy classification that is the symmetric spaces. So you don't really get an octonionic geometry that is analogous to Hyperkahler geometry. I mean, however, it is true, of course, you do have the two exceptional holonomy groups, G2 in dimension 7 and spin 7 in dimension 8. And some of the algebra of those, of course, is somewhat connected with the the algebra of the octonions. I mean, G2 in some sense is the symmetry group of the octonions. So there are some sort of shadows of octonionic algebra that do occur, especially in exceptional geometry and also for certain symmetric spaces, but there isn't really a big family like Kahler or Hyperkahler. Yeah. So the moral of the classification, Berger and Simons and so on, is that the holonomic groups of a Riemannian manifold are very, very restricted. You somehow have a generic case is the symmetric spaces, which occupy a special position in the theory. And then there's a very small list of other geometries, Hyperkahler, Kahler, quaternion Kahler, Ricci flat Kahler, Calabi-Yau, and the two exceptional geometries, and that's basically it. Yes, so the holonomic group is extremely constrained, but it's just this a generic case and this short list of special geometries and the symmetric spaces, of course.
And all of these at least all of these Hyperkahler ones, can I write them as algebraic varieties over the complexes?
Right, so a Hyperkahler manifold, of course, has a whole family of complex structures, and that's actually, so IJK, and that's actually important because it means it can be viewed as a complex manifold in different ways. And sometimes, so this is often the case for monopole moduli spaces or norm equation moduli spaces, sometimes those complex structures are all equivalent. Sometimes there's a natural spatial SO3 action that rotates one complex structure into any other one. In a monopole case, that arises from physical considerations. But there are other cases where the IJK may really be distinct. And it quite often happens, a simple example actually is a Gucci-Hansen. So for a Gucci-Hansen, somehow the generic complex structure is the complex structure of an affine variety. So x, y equals quadratic in Z. But then there's a distinguished complex structure, which is the one we have here, the cotangent bundle of CP1. And of course, because that has a non-trivial compact complex submanifold, it has that CP1 divisor, then it cannot be an affine variety. So that's a good example where the same Hyperkahler space can occur in different, really genuinely different complex guises. It can occur as an affine variety and also as a non-affine variety with a divisor. And that kind of thing happens in a more sophisticated way with things like the Hitchin space, spaces of Higgs pairs. You get a very similar picture. You sort of have a generic complex structure giving it an affine variety, but another complex structure giving you a completely different picture, sort of vibration with compact complex submanifolds.
Thank you. Any other questions? If not, we can take a fairly long break for coffee. So let's thank Professor Danster again.
Thank you.